So this is the third video for the section, and we're just going to wrap up with an example here about, for sketching this function using the first and second derivative test, and then after which you're going to have a short activity to do at your tables, and then you should be able to tie up all your loose ends with the day 1 and day 2 homework. There is only 2 homework assignments for this section, even though we're taking 3 days to cover it. So let's take a look at this function. We have a function minus 2x cubed plus 6x squared minus 3. So we have the function, which means we can plot the mins and maxes. So if you're really that type of person that really wants your mins and your maxes in the right spots, you can do that on this one. But we're gonna sketch a possible graph, so we don't really have to nail down those mins and maxes if we don't want to. So our first, you notice the approach isn't changing here, right? We're gonna find the intervals on which f is increasing and decreasing. In other words, we're gonna do the first derivative test, so we can find our mins, maxes, and now we know about plateaus. See if we have any of those. And so let's get that set up first with our first derivative test. So we have our number line set up, we have our axes set up here. So looking at this, here's the derivative, right? We bring down the 3, we've got negative 6x squared. Bring down the 2, we've got plus 12x, and the derivative of negative 3 is 0. So here's our first derivative. Let's set that equal to 0. Let's go ahead and factor out a negative 6x, right? We've got a negative 6 in both terms, we've got an x in both terms. That's factored out. So we end up with negative 6x times x minus 2, right? If we factor out a negative from 12, we're left with a negative 2 inside the brackets. So a quick distributive property just to check to make sure we did that correctly. Probably wouldn't be a bad idea. Okay, so that means x is either equal to 0 or to solve this, x is equal to 2. So there's my 2 critical points at x equals 0 and x equals 2. So right here and here on the x-axis. So let's go ahead and get those critical points down on our derivative graph. Okay, so we've got our critical points down. Now let's go ahead and test these 3 regions to see if we have positive or negative values for our derivative. So here's our derivative. Let's go ahead and test negative 1. So when we throw negative 1 here, we get negative 6 times negative 1 squared plus 12 times negative 1, right? Here it is right here. Negative 6 times negative 1 squared plus 12 times negative 1. So this is negative 6. This is negative 12. Altogether, we've got a negative 18. So that's a negative value. So we have a decreasing function in this region. Okay? Let's go ahead. In this region, let's test 1. So we plug in 1. That gives us negative 6 times 1 squared plus 12 times 1. So this whole thing is negative 6 now. This whole thing is positive 12. That gives me a positive 6. So it looks like that's positive and it's an increasing function. So if we go from a negative, I'm going to draw with my cursor here. Negative means decreasing, right? So negative derivative, 0. Positive derivative means increasing. Let me draw that again. Negative to 0 to positive, we have a min, right? Anytime these signs switch, we either have a max or a min. If they stayed the same, that would be our plateau. So we have a min here. Where it is, we don't care. Bottom line. Let's look at this region here. I'm sure I plug in 3. Negative 6 times 3 squared plus 12 times 3. It's a negative number. That's all I know. I could do the math, but I know this is 36 and I know this is bigger than 36 because 6 times 9 has got to be bigger than 36 because 6 times 6 is 36. So this is an all over a negative value, which means I have a decreasing function here. So if I look at this critical point, drawing this with my cursor again, I have a positive increasing function, then I go to 0, and then I go downward for my decreasing function. So positive derivative to 0, negative derivative. So that must be a max, right? So looking at these critical points, looking from left to right on the number line, I go from positive to negative to positive. So that switching means I have mins and maxes. If I had like the last example where I had negative, negative, that'd be plateau. So negative to negative means I've got mins and maxes only. Okay? So we're done evaluating the first derivative. So we're going to repeat those steps now for the second derivative. Okay? Oh, I forgot this, right? We know we go from negative to positive, so that's definitely a min. We go from positive to negative, that's definitely a max. Okay, so let's go ahead then and with the second derivative test. Find the intervals where f is concave up and down. That's our second derivative test. So we're going to use our second derivative number line. So I wish I had the first derivative here, but we know the first derivative was negative 6x squared plus 12x. So taking the derivative of that would be negative 12x plus 12. Okay, our second derivative test says set that equal to 0 to find our points of inflection. So I set this equal to 0. In this case, I factored out a negative 12, so I'm left with x minus 1 in the brackets. So the only way this can be 0 is for x to be equal to 1. And so when x is equal to 1, I have a point of inflection here. So let's go ahead and get that on my second derivative number line. That's my 0, that's my point of inflection. So the question is, where's my smile, where's my frown? All right, so let's test over here. Hopefully I chose 0 to test. I did. So we're going to plug 0 into our second derivative. Negative 12 times 0 plus 12. See, right here, negative 12 times 0 plus 12. So this is 0. Watch your math there. That's 0 plus 12, that's 12. It's a positive value when we're right here. So that means I'm concave up right here. So I have a smile. And then on the other side of my point of inflection, I probably test point x equals to 2 here, guessing. Yep. So negative 12 times 2 is negative 24, plus 12 is negative 12. So that's a negative value. That means I'm concave down here in this region. I have a frown. Okay, so I've got everything annotated here. We can go ahead then and let's go ahead and sketch this possible graph. So again, I'm looking at this minimum point here. This is my minimum. I need a minimum point here. And so there's my min, right? I have a smile in this region, right? I'm smiling all the way up to here. So, so I just arbitrarily put my point here. And that's going to be the lowest point on my graph. And get the smile set up so that I can start drawing this curve. Go over to my other critical point where I have a max. So I'm just going to put the max up high. There it is. And I know this max, in order for this to be a max, it's got to be a frown. Right? Can't go higher than that because that's a max. So notice I'm in the frown area for my curvature or my concavity. And then right here I need a point of inflection. So somewhere between my smile and my frown. Notice this is exactly it in the middle again. We had that question in class, does the point of inflection always fall right in the middle? It's kind of looking that way. I honestly don't know the answer. I haven't really looked at it that close across all functions, but it's beginning to be pretty promising. So second derivative of 0, I'm going to arbitrarily put that point of inflection kind of halfway between the min and max. Seems like it would be a pretty logical place. The exact placement isn't important. We just need to go from a smile to a frown. That's the important thing. So getting this general shape then drawn in, here's my smile. Notice my function isn't exactly matching my little sketches, my guides here. That's okay. It doesn't have to. So in this region, right, all the way up to x equals 1, I've got this smile here, this concave up, this positive derivative. So I'm coming, notice my first derivative, I've got a decreasing function, that's the left-hand side of my smile, down to my minimum, and then my function starts to increase, right? That's what this is saying right here. But I'm still in the smile category, right? That's my function has to increase, that's the only way I can smile. And then this next region, I'm going to continue increasing, that's what this is saying, continue increasing my function value up to here. But in this region, I'm also here. I'm also in the frown region for my second derivative. And then this is my max. And then after which my function has to start to decrease. So a possible sketch would look something like that. Um, so, and just a quick conclusion here then, how can derivatives be applied to make connections to functions? The derivatives enable us to analytically determine critical points, maxes, mins, and plateaus. I probably should have added plateaus there. And points of inflection, our concave up and our concave down sort of curvatures that we need to draw these functions. Now, if you were with me in day 3, we have a matching game to play, and each table is going to get a bunch of cards, and they're going to match an equation with a verbal description or a written description, and then a graph of the first derivative and second derivative, and a graph of the function. So this matching activity took place in class, and after that matching activity, then we can go ahead and finish up both days of the homework, or take the proficiency quiz in Blackboard, your choice. But we should be able to wrap up section 4.3 at this time.